Hello, everyone. So today's topic is electromagnetic induction. It's probably one of my favorite topics because I don't know, especially Lenz's law. I just find it fascinating. Right. So, and I have done this webinar many times before, so you can always go back and watch. So I've chosen some questions to do today. They're not necessarily the hardest or the easiest. They're quite basic. They're quite standard questions that you would get. And we start with motional EMF. And you might know, you might not, but if you have a piece of metal moving through a magnetic field, let's say a piece of metal of length L moving at velocity V through a magnetic field, and the magnetic field is perpendicular to the rod. Okay, so we've discussed a velocity selector, I believe, in the last physics webinar, and this is something similar in a way. So when the rod is moving through a magnetic field, let's imagine we are looking at a single electron inside the rod. So let's say we have a single electron inside the rod. Now, using the right-hand rule, sorry, the left-hand rule, of course, if we can find the direction of a force on an electron, because it's an electron moving through a field, therefore it experiences the Lorentz force. Correct me if I'm wrong, but yes, it's the magnetic force, and so the the magnetic field is into the page. Now, with the velocity is to the right, but it's an electron. An electron moving to the right produces a current to the left. So there's a downwards force on the electron. So there's a magnetic force downwards. Now, you could imagine if the wire is full of electrons and you push these electrons downwards, you would have the bottom end of the rod begins to gain electric charge, negative electric charge, because the electrons would be pushed downwards, whereas the top of the rod won't become positively charged because there's a lack of electrons, effectively. Electrons have moved from the top to the bottom. Now, because there's an excess of negative charge on the bottom and excess of positive charge on the top, the electron will experience an upward force, which is an electrostatic force. Let's call it electrostatic force. Okay. Right. So the electrostatic force, now, obviously, if you think about it, if the Y is moving through a magnetic field at constant force, at a constant force, you'd have the electric force must equal to the magnetic force because it will be in equilibrium. So the electric force must equal magnetic force, and we know that the electric force is Q multiplied by E, where E is the electric field, and F, magnetic force, is Q VB. We know that. Then if you divide by Q, both sides of the charge of the electron, now we have the electric field. But we know that the electric field, the uniform electric field, if you put a voltmeter here that measures the EMF, then the electric field is the voltage EMF per length divided by length of the wire. Therefore, EMF divided by the length of the wire is VB. The EMF is VBL. And this is known as the motional EMF. Motional EMF. Have you studied emotional EMF in school? And do you understand it quite well? Okay, so we have a conducting rod. You can answer in the chat. You have a conducting rod of length 0.5 meters, 0.5 meters, moving with a constant velocity of 4 meters a second, perpendicular to uniform magnetic field. So there's a magnetic field here. Let's just draw it like this. Magnetic field, which is 0.6 Tesla. The ends of the rod slide on a frictionless, so the frictionless rails, forming a closed rectangular circuit. So there must be another end here. So basically, there's a magnetic field. And yeah, so it is moving. Cool. Now, because the rod is moving, there's motional EMF on the ends of the rod. So also the negative charge will gather on the bottom, as we already know, and positive charge will gather at the top. And therefore, you would have an EMF in the upwards direction. So you would have a current flowing through the wire, and in an anticlockwise direction. And the EMF we already know is VBL. Find the magnitude of the motional EMF. So that is motional EMF is this EMF caused by movement through a magnetic field. Like you can imagine an airplane. If an airplane is flying through the air and there is the magnetic field of the Earth, so there's a magnetic field of the Earth, and B, and the wings will one wing will become negatively charged and the other wing will become positively charged, and that's a voltage. And if you register that voltage with a voltmeter, that's motional EMF. Does that make sense? And for an airplane, it's quite small because the magnetic field of the Earth is small. Well, if you see, oh, pardon, it says I'm offline. So if the speed of an airplane is about 200 meters a second, the wingspan of an airplane is about 60 meters for a big plane, and the magnetic field of the Earth is approximately 10 to the minus 5 Tesla. So you can imagine minus 5 Tesla. So the EMF is approximately 200 times 60 times 10 to the minus 5, which is 12 times 1.2 volts. So not massive, right? Maybe you're right. 200 times 60 times 10 to the minus 5. Yeah, 0.12. Apologies. 0.12 volts. So yeah, that's quite small. Let's move this because this is an example. Airplane. Is it aeroplane or aero? What's the proper spelling? Aeroplane flying in Earth's magnetic field. Okay. So I'm assuming this is not too easy for you, right? Because I can. Okay, so VBL. So oh, this one might be 4 times 0.6 times 0.5. Yeah, it's 1.2. Wow, that is a coincidence. 1.2 volts. Find the if the total resistance of the circuit is 2 ohms. So the resistance, we can assume that there's a resistance here, which is 2 ohms. Find the current. So the current is obviously EMF divided by the resistance, which is 1.2 divided by 2 ohms. And that is going to be 0.6 amps. 0.6 amperes. Right. So you, you might ask me, but if the rod is moving, the rod is moving. Now current is flowing, so energy is being dissipated. Energy is being dissipated in the resistor. Energy is dissipated in the resistor. What is the source is that of that energy? Is the source of that energy? Do you know? Well, how do you mean? Like maybe the question is if the wire is moving and energy is being dissipated. Well, it's the energy of the wire. Well, not necessarily. It's not the energy of the wire. We have to push the wire. In order to move the wire, you have to apply a force. Force has to be applied to move the wire. Why? Because there is a magnetic force acting on the wire. The wire is inside a magnetic field, and there's current in the wire. That means that there is the motor effect. The motor effect will push the wire backwards. So the magnetic force, there will be a magnetic force pushing the wire backwards, and you will have to apply a force applied in order to resist that, right? In order to keep the wire moving at constant speed, you have to keep pushing it. So you're doing work. Work is being done, is being done by the applied force, and that's your source of energy. You're doing work, and then done, and that energy is dissipated through the resistor. So if you try to push a wire, you will feel resistance. You will have to apply force. It doesn't move by on its own. Okay. Um, pro Problem two, and this is a fun one. I actually enjoy this one very much. A rotating metal disc is a Faraday disc. So basically, if you have a metal disc and you spin it inside a magnetic field, there will be a voltage on the ends or between. There will be a voltage between the center and the edge of the disc. And this voltage you can register with a voltmeter. So if you connect a voltmeter like so, you will register a voltage. So we need to work out that voltage. To work out that voltage, we are going to say, well, let's take the disk and let's take a small section of the wire. So like a small section of wire. So basically, it is like a very short wire moving through a magnetic field. So there's a magnetic field going into the page. Well, doesn't matter. In and out, it's actually into the page. So we can see there's a magnetic field going into the page. And the wire is moving with velocity v. And the length of the wire is this. This is the length of the wire. And there will be an EMF. Well, let's not call it L. Let's call it dr. dr is the length of that wire. Okay, I hope that makes sense. So like if a wire is moving with a velocity v, there's a magnetic field B, and the length of the wire is dr, is the vertical height, then the EMF induced, the EMF between these, the EMF, well, small change in small EMF is VB dr, right? Using the same formula, right? Voltage is VBL, length of the wire. Voltage is DE. Small change. It's a small change in voltage. And then VB dr, and the length is dr. Okay, so we have this expression. Now we need to add, because why we can think of that this section consists of multiple wires of length dr. That means that the EMF is the sum of the small EMFs. Or in other words, EMF is the integral from 0 to r, where r is the radius of the disk, v, b, d, r. Now, one more thing. We know that the velocity is linked to angular velocity. V is omega r. So we can substitute that in here. So that's equal to integral from 0 to r, omega r, b, dr. So omega b, these are constants, 0 to r, r dr. This is the integral of this is it's a quadratic, so that's 1/2 r squared between limits 0 and r. So it's 1/2 omega b r squared. All right, so that's the EMF induced on the disk. All right, so the EMF, so A, the EMF is 1/2. Well, the integral of x dx, the integral of x dx is 1/2 x squared. Let's see. Okay. And EMF is 1/2 omega b r squared, which is 1/2 times 50 radians per second. And it is multiplied by b, which is 0.4 Tesla, multiplied by the radius, which is 0.2 meters. And we get something. This goes 0.1. 50 times 0.4, that's 20. 20 is 2 volts. Okay, 2 volts. And B, then we have if the external load resistance is 5 ohm, find the current. So the current is the EMF divided by the resistance. So it's 2 divided by 5, which is 0.4 amps. Okay. Nice. Then I wanted to talk about Lenz's law a little bit. So I am quite fascinated by Lenz's law. See if I can get a decent picture. Lenz's law. Do you understand Lenz's law? Do you understand what Lenz's law is about? Somewhat. Okay. Lenz's law. Lenz's law. Lenz's law says that the current in a conductor will be induced in such a way as to oppose the change that induced the current in the first place. The induced current will oppose the change of flux that induced the current in the first place. Okay, so imagine you have a magnet moving downwards. You have a magnet moving downwards. So magnet moving downwards. Moving downwards. So the magnetic field in the loop is increasing. Field in the loop increasing. The flux in the loop increasing. Now the loop does not like that change, and the loop will produce a flux in the opposite direction. The loop will produce a flux in the opposite direction. Because it does not like change. And so let's see what happens. So the magnet is moving down. There's a downwards field. This is the field of the magnet. Field of magnet. And the coil would produce a field in the opposite direction. Field of the coil. And using the right-hand rule, you can find the direction of the current. So because if the field is upwards, you take the coil in your right hand, and you can see that the field is up, so the current is anti-clockwise. So the current will flow through the coil anti-clockwise. Do you think you understand that? Current. Well, the loop doesn't change the flux. This is to do with conservation of energy. Okay, this is to do with conservation of energy. I'll explain in a bit about the conservation of energy, but let's. Do you understand that? Assuming it is true that the loop doesn't like change, do you understand that the current will be anti-clockwise? And anti-clockwise wise current. will be induced in the loop. And that's Lenz's law. Okay? Explanation. Shown. There are many different explanations. I'm going to use the energy consideration. Consider energy. Now, the magnet falls through the loop. The magnet falls through the loop, and a current is induced. Consider energy. So magnet falls. Gravitational potential energy turns to kinetic energy. Now, some of kinetic energy is used to produce a current. Because there's a current, the coil will heat up. The coil heats up. Therefore, you have kinetic energy transforming into heat. So, the kinetic energy has to decrease. Kinetic energy decreases. So the coil slows down the magnet. Coil slows down magnet. So if the field of the magnet is downwards, the coil will produce an upwards magnetic field. So it's an upwards force. So the field of coil must be opposite to field of magnet. Because alternatively, if the field was downwards, the coil would accelerate the magnet, which doesn't make sense because it contradicts the conservation of energy. That means the coil would push the induced current would use up kinetic energy to increase the kinetic energy of the magnet, which doesn't make sense. Do you think you understand? Yeah, so it has to be that way. Otherwise, conservation of energy doesn't work. Now, why this happens? Well, Richard Feynman famously said, we don't know how magnets work. They just do. And that's a fundamental law of physics. Anything else in the world can be explained with magnets, but not the magnet itself. The magnet is just there. It just is, right? Well, you can talk about magnetic domains and everything, but fundamentally, an electron has a magnetic field, and we don't know why. It just does. Okay, so or atoms have a magnetic field, and we don't know why. I don't know. I don't dig that deep into theoretical physics. Probably not my piece of cake. Yeah. Does it say it's not my piece of cake? I don't know. Right. So field, maybe we will. Field of coil must be opposite to the field of the magnet. Otherwise, it would accelerate. Otherwise, it would accelerate the rate. The magnet. Conservation of energy would be okay. Anyways, I'll move on. Changing magnetic flux in a coil. So a coil with 200 turns and area is placed into uniform magnetic fields. Okay, so there's a magnetic field. And there's a coil. So coil like this with many turns. And well, it doesn't have to be like this. It could be like this, two wires. For the magnetic flux through the coil changes from 0.1. So it's a variable magnetic field. So the flux 0 is, well, flux 1 Webers and flux 2 is 0.04 Webers uniformly, and the time is 0.1 seconds. Calculate the average induced EMF of the coil. Well, that's quite a straightforward question because we know that EMF is the minus the change in flux over change in time, but also N because there's N turns, N turns. So it's going to be minus 200 multiplied by the change in flux, which is 0.03 Webers over 0.1 seconds. So that should be 6 volts or 60. 200 times 0.03 times 10. 60 volts, minus 60 volts. Now, the minus doesn't really make sense because what do you mean by minus 60 volts? Well, it's just the minus just means that the current will oppose the change. So now we can see that the flux is decreasing. Flux is increasing. So coil will produce a magnetic field in opposite direction, and that means out of page. So the black is the field of the external, and the coil will produce a field out of the page of the coil. And using the right-hand rule, we grab the coil, so the field is towards our face, so the field is the current will be anti-clockwise. So the induced current will go in an anti-clockwise direction. Oh, of course. Oh, there's the magnetic flux. We don't need the area because flux is B times area. I know it's confusing, but we are given flux. So effectively this is extra information which we don't need. Okay. Yeah, so maybe it was the field. If the field changed from 0.01 Tesla to 0.04 Tesla, then we would use that. Then we would use the area. But because we're given the flux, then no, we don't need it. Okay. A little bit direction. I know it's confusing, but I don't know. It's a weird question. Direction out of the page, and that means that the current is anti-clockwise. Okay. Now in this assignment, we discover inductors. Inductors in inductors like is an inductance. Now, How does that work? So imagine you have a coil. Inductors, inductance. Imagine you have like a light bulb. Well, a light bulb is not a very good example. Okay, let's imagine you have a resistor. You have a resistor and you have a battery and you have a switch. And suppose you close the switch at some moment in time. How does the current change? How does the current change through time? So if you try to draw a graph of current versus time, then if the switch is closed at t0, switch closed, closed, you well, at least what you've been taught in school, that it has to be like this. It has to be exactly like this. But common sense tells you that that doesn't happen. That doesn't happen in real life. In real life, you would have something like this. It will be quick, but it wouldn't be instant. Now, what is the reason? Well, the reason, I mean, how can you explain that it will not be instant? Well, the explanation is in inductance. The wires have a natural resistance to change. Wires produce their own magnetic field, and that magnetic field induces a current in the opposite direction. So let's have a look. Imagine we have imagine we have a coil of wires. And we have a coil of wire, and we have a resistor, and we have a switch. When a current flows through the coil, the coil produces a magnetic field. When the switch is closed, the switch is closed. There is a magnetic field. The magnetic field, there is a current. There is an increasing current in the coil. A coil is literally a coil of wires. There's an increasing current in the coil. This means that the flux in the coil is increasing. Then this means that the coil will induce a current in the opposite direction. This will decrease the rate at which the current is increasing. Let's look at an example. So FET AC circuit. I hope this one works. Yes. So let's take a battery and a resistor and an inductor. And we're gonna have a large inductance, wire, switch, wire, resistor, wire, resistor. And I'm going to measure the current as a function of time. Okay, this is 10 ohm. This is a 9-volt battery, so the maximum current is going to be what? 1 amp. Let's reduce the current resistance to reduce the resistance to 5. Okay, so it will be just under 2. Right, so let's switch on the circuit. And you can see that unlike what we expected, the current builds up slowly, reaching, well, terminal value. Once again, close the switch. So let's remove this, by the way. Let's remove this coil and see if there's any difference. So 3, 2, 1, up. You can see it's a step. It goes from 0 to 2 amps almost instantly. Well, instantly in this case because, well, it doesn't, the time is too short to notice. But if you add a coil with no resistance, by the way, there's no resistance in the coil, is just a magnetic field which slows down the buildup of current. Watch again what happens. The current builds up slowly. Okay, I'll reduce the inductance because it's just too slow. Let's make it 5. Okay. Once again, 3, 2, 1, go. And you can see that the current builds up slowly. And this is due to Lenz's law. So once again, you close the switch, the current is increasing. The increasing current induces the flux in the coil, and the coil generates a current in the opposite direction to oppose the change that produced it. That's pretty cool. Like, I don't know how about you, but I find it fascinating. It slows down, and all wires have inductance, not just coils. All wires have inductance, but the coily wires have more inductance. They're more resistant to change. That's why you don't really notice it with straight wires. With straight wires, you just flick it on and it's on. But if you had a coily wire, that would slow down the buildup of current. That would, yes. And that, and another reason, like if you take an electric motor and switch it on, when you switch an electric motor, so electric motor graph of current and versus time. This is another thing. When you switch on, when you flick the electric motor, it's a coil. It's a coil inside a magnetic field. But initially, the coil is not rotating when a motor is switched on, the current is maximum. As the coil rotates, a voltage is induced. A current is induced in the opposite direction. Thus, reducing the overall current. So because a motor is a motor can be used as a generator, and the generator can be used as a motor. When a motor starts spinning, it becomes a generator and it generates a current. But because of Lenz's law, it generates a current in the opposite direction, and that reduces the current in the motor. And that's why if you take an electric motor, if you take like a toy electric motor, like this one, it's a toy electric motor, and you connect it, it will start spinning. But if you hold it with your hand whilst the current is still flowing through the coils, that usually burns down the motor. I did this with a very expensive toy train. My parents were very angry with me when I was 12 years old. I had a toy train and I switched it on and I blocked it with, I don't know, another toy. And yes, it burned down because it was not spinning. And if it wasn't spinning, the current stayed at its peak. So this is not spinning. Spinning. So if you hold an electric motor, the current will be too high and it will probably burn down the motor, as it can happen. Anyways, cool. Toy trains used to be very expensive. Like, I think it was something like several days' wages for one of my parents. Anyways, yeah. So the inductance is measured in um, is in Henry, and L is inductance. L is inductance. Inductance. And if you have if you have a coil of wires, then the EMF induced in the coil is minus, of course, because it's in the opposite direction, L di dt. So di dt is the rate at which the current is changing. And L is an inductance which depends on the geometry. Depends on geometry of the coil. So the number of turns, the length, the diameter, etc. Okay. The more turns you have, of course, the bigger the inductance. So what is an inductor? Electric inductor. It looks like this. You might have seen it if you've ever taken apart a computer or anything like this. You would see those induction coils. Or like this. This is an induction coil. This is a school induction coil. Yeah. So yeah. Nice. An inductor of inductance 0.3 is in series with a resistor of resistance 20. So we have an inductor and is 0.3 Henry. And we have a resistor with resistance 20 ohms. The current decreases uniformly. Oh, that's a boring question. I thought it was more exciting. Okay. Okay. you have the current. We don't know what's happening here, but we know that there's a current, and the current changes through time. The current changes through time, and we know that the voltage induced in the inductor, so the voltage induced in the inductor is minus L, which is the inductance, multiplied by di, the change in current divided by change in time. And that is minus 0.3 multiplied by current, by the current, which is from 0, so 3 amps. Final, so 0 minus 3, 0.05 seconds. And because it is minus 0.9 divided by 0.05 seconds, which is volts times Henry. So 0.9 divided by 0.05, 18. Oh, there's plus 18 volts. Now, because this is question A. B, does the induced EMF aid the current or oppose the decay? Well, it's a decreasing current, and coils don't like change. So the voltage will try to increase the current. So the voltage would be induced helping the current. So the current is decreasing. The coil will try to increase the current, increase it. So EMF is induced in the positive direction. Okay. And I think it's I think we can do a more interesting question. Draw a graph. So find the equation. So that's problem 4A. Let's call it 4A. Find current in the circuit as a function of time. And it's the same circuit, and it's a 20 ohm resistor, and the inductance is still 0.3 Henry. And let's say we have a battery which is 10 volts, EMF 10 volts, like this. And there's a switch. There's a switch that is closed. Okay. So we know that the voltage on the resistor is current times resistance, of course. We know that the voltage on the inductor is minus L times di dt. Okay, so when you close the switch, the current will be increasing. The current is increasing. So the inductor will produce a voltage in the opposite direction. So it will produce a voltage in this direction. So it will try to push electrons backwards, counterclockwise, whereas the battery is pushing clockwise. So battery is pushing clockwise, the inductor will push anti-clockwise, and the resistor is just a resistor. Well, the resistor reduces the voltage as well, so it's going to be plus and minus here. So plus means high potential and minus means low potential, so hope that makes sense. So current will flow from high potential to low potential. And so now we can write Kirchhoff's second law. Kirchhoff second law is that the potential difference, the sum of potential differences across a circuit, the sum of potentials across the circuit is 0. And that means that the battery increases the potential, so plus EMF. The inductor takes away minus voltage on the inductor and minus voltage on the resistor. I'm going to take the modulus because the inductor, we already said that it's minus, but what does the minus mean? What is, we haven't defined a positive direction. So oh, okay, we can say that the voltage on the resistor is minus. So minus means energy sink. Okay, minus means energy sink, and plus means energy supply. So energy supply minus energy sink is 0. I hope that makes sense. And now we substitute EMF equals minus L di dt minus IR equals 0. And we can write L di dt equals I EMF minus IR. Now, this is a differential equation, so I divide both sides by EMF minus IR. So L divided by EMF minus IR di equals dt. And now I can integrate. Time changes from 0 to t, and current changes from 0 to I. Okay. Now, if you recognize this integral, very good. If you don't, well, you actually should. It's a logarithm. It's L multiplied by logarithm of EMF minus IR. Now, do we need a minus there? We do. There's a minus. And do we need a... Yes, we need an R as well. So minus 1 over R. Yes. Okay, that makes sense. And that's equal to T. T between limits 0 and T. And this is between limits 0 and I. Now I integrate this, minus L over R multiplied by logarithm of EMF minus IR. Now this is a positive value, so I don't need modulus anymore because EMF is greater than IR. Minus logarithm EMF because I is 0 and then equals T. And then I combine this two, I multiply by R, so EMF minus IR divided by EMF logarithm equals minus TR over L. And then EMF minus IR equals EMF multiplied by e to the power minus TR over L. And finally, I get current is equal to EMF divided by R, open bracket, 1 minus e to the power minus R over L T. And let's see if that makes any sense. So current versus time. So current versus time is EMF is 10 volts divided by resistance, which is 20. 1 minus EMF E minus R, so that's 20 over L, 20 divided by 0.3, that's what, 20 divided by 0.3, 66 minus 66.7 t. Okay, which is 0.5 multiplied by 1 minus e minus 66.7 t. Let's sketch that graph, t and I. You see how physics becomes super exciting when you add a maths element to it. So it starts from 0, because when t is 0, this is 1. So 1 minus 1 is 0. And then it is an inverse. So it's going like this. And the final current is 0.5 amps. Let's see if that makes sense. So let's say, Henry, can I change it to 0.3? Oh, come on. Yep, 0.3. Now the resistance is 20. And the current voltage is 10. Okay, open, play, and bam. Okay. Yeah, pretty much, except, well, yeah, we've reduced that graph. Okay. I don't think I'll do question 5. It's a bit too much detail in there, and I think I've done a very similar question before. So, I think I'll stop here. I hope that was useful. I hope that makes sense. We'll do a lot more differential equations next physics session, because the next topic is my absolute favorite, is RLC circuits. And I just a sneak peek into next session, into next physics session, of course. So imagine you have a capacitor and you have a coil. Now, when, of course, you need a switch, because without a switch, it just doesn't work. You have a capacitor in the coil, and imagine the capacitor is charged. When you close the switch, the current in the coil will increase, but coil doesn't like that increase, so the current will build up slowly. Current in the coil through versus time. But then once the capacity is discharged, the current will drop. The current will start dropping, but the coil doesn't like change. So it will try to keep the current running for longer. And actually, what happens is it will run the current for longer, and then the current will go back up, and like this. And these are called this is called an oscillating circuit. So this is what we are going to do next time. An oscillating circuit, and the versus time. Let's have a look at an oscillating circuit. So let's take a capacitor. Okay, we'll need to restart everything. Take a capacitor. Let's make the capacitance as large as possible. Okay, not Very exciting. Okay, to increase the capacitance, we can double up. So doubling up the capacitance. So that's 2 capacitors. Yay. 2 capacitors increase overall capacitance. Because it's like a capacitor with bigger plates. And okay, then we need an inductor. And we need 2 switches. One here, one here, and here, one here. We'll need the inductance as large as possible, and we'll measure the current. Now, the current, well, let's see what we get. Take a battery and connect the battery here. Okay, so first we will charge the capacitors. So you can see I've charged the capacitors. Now the top is positively charged, the bottom is negatively charged. I've disconnected the battery. So now I'm going to discharge the capacitors through a induction coil. And you can see that the current reverses. The current goes back and forth, back and forth. This is what we call an oscillating circuit. It's a bit, okay. We can change the inductance to something. Maybe reduce the capacitance. Okay, that's better. We've just created an AC current. So I hope you like that. All right, I'll finish here. I'll see you all. When do I see you? Well, let's check. Let's check. Webinars. Year 13 webinars. Next session is on the 4th of December. 4th of December, and that's 3D geometry. And then it's the 18th of December, and it's the circuits, so, which is exciting. All right, I'll see you all on the 4th, and yeah, see you.